So, dear students, welcome to another lecture of Basic Electrical Engineering. In this particular lecture, we will understand the concept of efficiency in the electrical transformers. So, this lecture is dedicated to uh, the transformer efficiency. Then we will see what is the condition for maximum efficiency in transformer, and then we will understand what is all day efficiency. So now, as far as efficiency is concerned, so the efficiency of a transformer at any particular load or power factor is the ratio of power output to the power input. That means efficiency generally depends upon the load and the power factor of the transformer. So for different types of loads, for different power factor values, the efficiency value could be different. However, in general, the efficiency is always the ratio of the output power of the transformer to the input power. So as you can see in this equation, efficiency is output upon input. So here output signifies the output power and input signifies the input power, right? So now, as we know that the output of a transformer is basically uh, in uh, generally the rating of the transformer is always in volt amperes. However, when we study the efficiency of a transformer, it is always studied in watts, right? So it is always calculated uh, by taking the power in terms of watts instead of generally volt amperes, right? So, as we know that the input of the transformer means whatever input we give to the transformer or the input power of the transformer, it gets divided into two components. The first is the output power. The output power is generally the useful power which is utilized for some purposeful work, and some part of this input power is wasted in the losses, right? So this has two components, output power or and the losses. Or you can say, so whatever energy, whatever input power we give to the transformer, it is converted into output power, as well as some of the power, some of the input power is wasted in the losses. And we know that there are two types of significant losses. However, there are many types of losses, but the significant losses are the copper losses and the iron losses. So among these two losses, copper losses are basically the temporary loss, and iron loss is basically the permanent loss in the transformer, right? So now this is one way of writing the efficiency. The another way of writing the efficiency is, because we know that input power is output power plus losses. So we can write it in other way, and that is we can write it in terms of the input power and losses instead of writing it in terms of output power and losses. So output power is input minus losses, right? So this is what is given here. Okay. So instead of writing output, we will write input minus losses. So simplifying this equation, so we will get 1 minus losses by input, right? Now, as you can see here, if the input power and losses, if input is equal to losses, then efficiency is 0, right? So uh, if losses are 0, then efficiency is 1 minus 0, 1, that is 100%, right? So these are the two cases. Okay. So efficiency can be 0 when all the input power is totally converted into the losses. That means all the input power has been wasted in the losses. And the second is if losses are 0, so in that case efficiency is 100%. However, these both are hypothetical cases. So that means we cannot have the 0 efficiency all the times. We cannot have the 100% efficiency. So there is a condition for the efficiency to be maximum, right? Now, efficiency, as I already discussed with you, that efficiency is based on the wattage, not on volt amperes, though the unit of the rating of the transformer, the rating of the transformer is in volt amperes. However, the efficiency is calculated or obtained in wattage, right? So if we have the because the efficiency depends upon the load, right? Okay, and the power factor also. So if we have the unity power factor of the transformer, in that case we have the maximum efficiency or more efficiency of the transformer, right? Now, how will we calculate the efficiency of the transformer? As from these two equations, right, you can simply make out that to calculate the efficiency of the transformer, you need to know the output power, you need to know the copper loss, you need to know the iron loss, right? So, or you can say that you need to know the input power and the losses. So if you know these parameters, it is quite easy for us to calculate the efficiency of the transformer. However, to calculate the copper loss, we need to perform the short circuit test on the transformer, and to calculate the iron loss, we need to perform the open circuit test on the transformer. So these two tests basically will give us the amount of um, copper and iron losses that occur in the transformer, right? So now, so there is a condition for the maximum efficiency. So now that condition will be understood in the next slide. However, graphically we have represented it in this way, right? So the efficiency would be maximum at some, load. Now, what shall be that load? What shall be the losses? What shall be the output power? So that we will understand in the next slide, this slide, right? So now let us see what is the condition for the maximum efficiency. As per the statement, in any electrical transformer, the maximum efficiency will occur only when the two significant losses, that is the iron loss and the copper loss, are same, are equal. So as per the definition, these two losses must be equal to have the maximum efficiency of the transformer, right? Now, so the iron losses in the transformer are given by Pi, so which iron losses basically are because of the hysteresis loss and the eddy current loss in the transformer. So Pi is equal to Ph, where Ph is the hysteresis loss and PE is the eddy current loss, right? Similarly, the copper loss, which are also known as the winding losses, right? Okay, so it is given by PCU or PC, right? This is just a notation. PC, P for power basically, because these losses are always measured in wattage, right? In watts basically. So P indicates the power dissipated in form of loss. C indicates copper, or Cu also indicates copper. Similarly, here this P indicates the power dissipation in terms of loss, and I indicates the iron. Iron losses are also known as core losses or permanent losses, right? Similarly, these copper losses are also known as winding losses or the temporary losses. So there is a reason behind it. Why do we call these losses as either permanent losses or the temporary losses, right? Now, let us proceed further. So let us find out the proof. Let us prove this condition, whether this condition is true or not, whether the statement is true or not. So let us prove this one. As we all know that the power that is input to the transformer is given by V1 I1 cos phi 1, where V1 is the RMS value of the input voltage, that is primary voltage. I1 is basically the primary current, and this phi 1 is basically the phase difference between these two quantities, right? So, and the output power is given by V2 I2, where V2 is the terminal voltage, load terminal voltage, and I2 is the load current, and phi 2 is the phase difference between these two quantities, right? So efficiency is generally determined when the transformer is under operation. It is working, right? So when it works when it is loaded. Okay. So when the load is connected to the secondary winding. Now, what is efficiency? Efficiency is generally denoted by the Greek letter neta. So it is input power minus losses divided by input power, right? So it can also be written in terms of the respective equations, like input power is V1 I1 cos phi 1, right? So minus PCU, because there are two types of losses, significant losses. These are the copper losses and the iron losses. So we will write losses as means these are subtracted from the input power, right? So divided by input power. Now, if we simplify this equation, we will get efficiency equal to 1 minus the sum of two losses and divided by the input power, right? Now, now we can further simplify this equation by simply dividing V1 cos I1 cos phi 1 with every loss, copper loss and the iron loss. So in this case, PCU is basically the copper loss and PI indicates the iron loss, right? Where PCU can also be written as I1 square into R1 or I2 square into R2, because the copper loss indicates the winding losses. Now, if we substitute uh, PCU in this equation, okay, so since we have taken the input power here, so we will take I1 square into R1, right? So when we put it here, so we will get this equation, this one, 1 minus I1 square R1 divided by the input power minus iron losses divided by the input power. Then we can see that one I1 will be cancelled out here, right? So we have cancelled out this I1 in the denominator and the numerator. So we have another equation which is indicated as equation number 1. So here the efficiency is 1 minus I1 R1 divided by V1 cos phi 1 minus Pi, where Pi indicates the iron losses divided by V1 I1 cos phi 1. Now, If we differentiate this equation 1 with respect to the primary current, that is I1. Okay, so because we have taken this I1 to be uh, an independent quantity in on which the efficiency depends, right? And we know that this I1 also depends upon the value of I2. How? Because if there is any variation or change in the secondary current, it will in turn affect the primary current, right? And the value of I2 always fluctuates with the load fluctuation. If load is varying, in that case, the secondary current would also vary. So if we differentiate that equation 1 with respect to I1, so we will get this equation here. So the first term of the previous equation will become, this is 0. So this is with respect to I1 will be R1 divided by this. And then we have the next term also, right? So this is how it will come. So this F1 is generally phi 1. So this is simply a typo mistake here. So it is phi 1, right? Now, there is a condition for maxima. We will apply that condition for maxima here. And the condition for maxima is that the first derivative of efficiency with respect to I1, with respect to this quantity, should be 0. And the second derivative must be negative. So when we do so, we will get, so we will put this term equal to 0. So by putting this term equal to 0, this is already 0. So we have this part is equal to 0, which is shown here, right? And by equating these two terms, we have got this one. And similarly, we'll keep on simplifying this equation because here we know V1 will be cancelled out, cos phi 1 will be cancelled out. So we have R1 is equal to Pi divided by I1 square. So when we simplify this one further, means we multiply it here. So we will get I1 square R1, or because we know that if we do it in terms of I2 instead of I1, we will get this equation on this particular side, right? So I1 square R1 is equal to Pi, right? So what is I1 square R1? This is nothing but the copper loss, right? So hence it is proved that the copper losses equal to iron losses will give you the maximum efficiency, okay? So to get the maximum efficiency, what we have done, we have applied the condition for maxima actually there. Now to apply the condition for maxima, we need to find out the first derivative of the efficiency, which we have obtained here. And then the second derivative must be negative. So if you find out the second derivative of this equation, it will be negative, right? Because this I2 square is in denominator, so it will give you a negative result. That means both the conditions are being fulfilled here. So we will put this equal to 0. Now, when we have put this equal to 0, on simplifying this equation, we have got that the copper loss is equal to iron loss. Now, at maximum efficiency, what will be the copper losses? The copper losses will be equal, sorry, not the copper losses, the current that flows in the secondary winding, the load current. Now the load current is nothing but the I2. So the value of I2 or the expression for I2 at maximum efficiency will be this one, right? How did I get this one? By using this part of the equation. So this will give me I2 square into R2 is equal to Pi. So here I2 is equal to Pi by R2 and square root. So this is what I have got here, right? Now let us proceed further. Now this was about the condition for maximum efficiency. And we have seen that yes, it is true that the maximum efficiency occurs in a transformer when the two significant losses, that is the iron losses and the copper losses, are equal, are same, right? Now we will see that how this efficiency varies with the power factor, because in the statement we have already mentioned that for a particular load and particular power factor, yet any or at any power factor or at any load, the efficiency is defined by the ratio of these output power to the input power. So let us see what effect the variation in power factor put on the efficiency. So as we know that the transformer efficiency is given by this equation, right? We have already seen this in our previous slides, right? Now, if we simplify this equation, we will get this one because input by input is 1 and then minus losses by input, right? So losses we have written here. So input we know that it is equal to the output power plus the losses because we know that input power divides into two components. One is the output power and second one is the losses, right? So we have written it here. Then we can simplify this further. So we will divide this with this because cos phi we know that this cos phi is nothing but this is cos phi 2. Okay, this is phi 2 basically. So phi 2 is the phase difference between V2 and I2 where cos phi 2 is cos phi 2 or you can say cos phi also doesn't matter. It doesn't matter, right? Or doesn't matter. This is the secondaries power factor, right? This is a secondaries power factor. Now, so let us see further. Now, so if we replace this losses by V2 I2 with some factor beta, this is some arbitrary factor. Okay, you can replace it with any notation X, Y, Z, A, B, C, D, F, whatever, right? So we have taken beta just to have a distinguished notation, right? So if we do so, so we have efficiency is equal to 1 minus beta because losses by V2 I2 we have taken as beta. So it is beta by cos phi 2 plus beta. Now, if you see this particular equation, this one, okay, this could be, let us say, some equation number 6 or fine, whatever. Now, if you see in this equation, a cos phi, this power factor, this is the power factor, right, of secondary. Now, this power factor is in denominator. So, if this power factor is 0, for example, if cos phi 2 is 0, that means hypothetically it is minimum value, right? So in that case neta will be equal to b 1 minus beta divided by 0 plus beta. So this will be 1 minus beta by beta, so it is cancelled out 1. So neta is equal to 100, sorry, 0. So 0 means that uh, the efficiency is 0, right? So if cos phi 2 is 1, so denominator part is maximum. So when denominator part is maximum, right? So if you see here in this, so let us rub this, right? So now the second case is if cos phi 2 is 1, right? So when will be cos phi 2 1? For the resistive load, right? So if this is 1, in that case, we have neta is equal to 1 minus beta divided by 1 plus beta. So in this case, this part is greater than this part. So that means overall this would be less. So neta is maximum, right? So that means as cos phi 2 increases, right, efficiency also increases. So let us see This in terms of a diagram. As you can see here in this particular diagram, as the power factor, here we have zero point 0.6 power factor, then zero point 0.8, then 1.0. This is the unity power factor. So as the power factor is increasing, we can see that the maximum efficiency is increasing. So at unity power factor, you have almost more than 98%, right? You can see it is almost more than 98% of efficiency. So that is why it was mentioned in the first slide that for the unity power factor, the maximum efficiency would occur. There are two things. Don't get confused with this one. One is the condition for maximum efficiency. The condition for maximum efficiency will always be same for whatever power factor is there, right? Whatever power factor. But within the power factor values, if you compare with respect to power factor, so the low power factor will give you low efficiency and high power factor will give you high efficiency, right? So this was about the efficiency of the transformer, and we have seen how the efficiency varies with the power factor, right? Now, let us come to the all-day efficiency. Now, what is all-day efficiency? Generally, efficiency of a transformer is measured by taking the ratio of the output power, which is in watts, to the input power, which is in watts. This is the ordinary efficiency. Now, as we all know that the transformer, right, has two windings. One is primary winding, which is connected to the supply. This is V1, and here we have some impedance Z1, right? And then we have E1, which is induced EMF in the primary, right? And then we have some flux flowing here, phi. Then we have the secondary winding, and we have a impedance at this one, which is Z2. Then we have a load connected here, right? ZL load, right? So here I have V1, V2 as the terminal voltage, and here I have E2 as the induced EMF, right? And the current here is I2, and the current in primary is I1, right? Now, when there are two things basically, one is the ordinary efficiency, the second is all day efficiency. Now what is all day efficiency? As you can see from the all day means the efficiency of the transformer for 24 hours. Within 24 hours, what is the efficiency of the transformer? Now because a transformer, there are two cases. Case one, transformer on no load. So in this case, primary is connected to the supply, but secondary is not connected to load, right? So that means primary current will keep on flow. So in this case, I1 will be equal to I node, that is the no load current. So in this case, iron losses exist, but copper losses are neglected, right? Now there is a case two. Case two is when transformer is loaded. So in this case, I1 and I2 are supposed to flow at full load rated value, right? Pi exists as well as PCU exist. Now, what is the purpose of writing these two cases? The purpose is to make you understand that a transformer is not connected to load all the time, right? A transformer is not connected to load all the time during a day, right? So now, if it is not so, then that means the losses in the transformer will vary, right? Iron losses because are permanent losses. So whether your transformer is connected to load or not connected to load doesn't matter, right? Iron losses will be there. They exist in both the cases. But we have seen that the copper losses depend upon the load, and hence when the transformer is connected to load, copper losses become significant and hence they are considered, while when the transformer is not connected to load, the copper losses are insignificant and hence they are neglected. So all-day efficiency is basically the ratio of the electrical energy. This is kilowatt hour, right? This is the electrical energy which is delivered in 24 hours divided by the electrical energy input in the same time, that is the electrical energy, that is the output. This is basically the output, right? Delivered means output, right? So the amount of electrical energy that is consumed in 24 hours divided by the amount of electrical energy that is supplied, right? Okay, means the input at the transformer is will give you all day efficiency. So all day efficiency is the output power in kilowatt hour. Kilowatt hour is the unit of electrical energy, right? And divided by input in kilowatt hour. Now, as I have just discussed with you all that uh, the transformer is generally not connected to load all the time throughout the day. There are certain durations, certain instants for which the transformer load is disconnected due to any reason, right? So the load keeps on varying across the secondary of the transformer, right? So this would, uh, you know, result in the overall, variation in the overall efficiency of the transformer, right? Now, because the primary, as I just discussed, primary is connected to the supply, so core losses, that is the iron losses, this is the iron losses, right, will always be there for the continuous time, right? However, we need to take care of the design aspect of the transformer, that uh, the transformer must be designed for minimum iron losses, right? Because they are permanent losses, right? Now, because copper losses are uh, based on or dependent on the load fluctuation, so they are quite less important as compared to the iron losses, right? So now if we have to calculate the all day efficiency, we need to know that how the load is fluctuating in case of the transformer, right? Or how the load is fluctuating across the secondary of the transformer on hourly basis. So if we can do so, so we can get the all day efficiency by using the above given expression. So this will give us all day efficiency, right? So dear students, in this lecture we have gone through the concept of efficiency of the transformer. The efficiency is simple. It is the ratio of output to the input, and it is always measured in terms of it is a percentage, basically a ratio of two watts, right? Output wattage and input wattage. So input, the power input to the transformer gets converted into the useful power at the output, and the losses, some of the power, input power, is wasted in losses, right? And the significant losses are the copper losses and iron losses. So so this was about the uh, today's lecture, and thank you so much.